Welcome friends, Igor is here, and in this video we will classify all finite dimensional vector spaces. In this lesson we will prove that vector representations are invertible linear transformations, prove that a vector space of dimension n is isomorphic to Cn, and prove that all finite dimensional vector spaces are classified by their dimension. Let's get started. First, let's prove that vector representation is an injective linear transformation. Say we have a vector space U of dimension n, and we take a basis B of this vector space. Once we fix the basis, then we can construct a vector representation function ρb from the vector space U into the vector space of column vectors of size n. We have defined this function in the last video. We then also proved that this function is a linear transformation, so the only statement we need to prove here is that it is in fact injective. Let's take any vector u in the kernel of this linear transformation. This means ρb sends u to the zero vector in the codomain. By the definition of the function ρb, the components of the vector ρb of u are the scalars in the presentation of the vector u as a linear combination of the vectors in the given basis B. But the vector ρb of u is the zero vector. All its components are equal to 0. Multiplying any vector by zero scalar results in a zero vector in any vector space, therefore all of this simplifies to the zero vector. This shows that u is the zero vector and therefore the only vector in the kernel of ρb is the zero vector. This means the kernel is trivial and therefore ρb is indeed an injective linear transformation. Second, let's prove that vector representation is a surjective linear transformation. Once again, to define a vector representation, we need to fix a basis B of a vector space U, and we already know vector representations are linear transformations, so the question here is why it is surjective. Let's take any vector v in the codomain Cn. Then we are going to construct a vector u in the domain u as follows. We are going to use the components of the vector v, which is a column vector, as scalars in the linear combination of the vectors of the basis B. Then, by the definition of the function ρb, the value of ρb on the vector u is the given vector v. This shows that every vector in the codomain is a value of ρb, therefore ρb is surjective. And now let's prove that vector representation is an invertible linear transformation. We have done all the work for this proof already. We established that a vector representation is injective and surjective as a linear transformation. But this means it is invertible as a linear transformation. And this is exactly what we are trying to prove. So, vector representation is an invertible linear transformation from the given vector space to the vector space of column vectors. So, when we apply this function ρb to the vectors in a given vector space, we will get column vectors, and components of that vector we can think of as coordinates. For this reason, application of the function ρb will be called coordinatizing a vector. But it also has an inverse linear transformation, ρb inverse. It takes a set of coordinates and reconstructs a vector with these coordinates. The process of applying this inverse function will be called uncoordinatizing a vector. And now we have arrived to a very interesting place in this course. We started by working with some explicit objects, such as column vectors or matrices. We defined specific operations on those objects, such as addition of column vectors, addition of matrices, scalar multiplication of column vectors, and scalar multiplication of matrices. But then we observed that these operations on different kinds of objects satisfy identical properties. This prompted us to generalize this idea and define the notion of an abstract vector space. But now we are going to go back to the starting point. we are going to prove that every vector space of dimension n is nothing but a copy of column vectors simply viewed from a different perspective. Every vector space of dimension n is isomorphic to the vector space of column vectors of size n. We have a vector space V of dimension n, and so we can choose a basis B of this space, which contains n vectors. This allows us to construct a vector representation, rho B, which is a linear transformation that goes from the vector space V into the vector space of column vectors of size n. We just proved that this linear transformation is invertible, and therefore the vector space V is isomorphic to Cn. This isomorphism is achieved by this vector representation. Here are some examples. A vector space of polynomials of degree at most 5 has dimension 6, therefore it is isomorphic to C6. Vector space of matrices of size 3 by 5 has dimension 15, therefore it is isomorphic to C15. If that's not enough, let's recall the crazy vector space, which is a vector space of dimension 2. This crazy vector space is nothing but a weird way of looking at the column vectors of size 2. And finally, we are ready to enjoy the ultimate achievement of linear algebra. The ultimate goal of any mathematical discipline is to classify the objects of its study. Linear algebra studies finite dimensional vector spaces, and it is possible to completely classify all finite dimensional vector spaces. Few mathematical disciplines can boast this kind of achievement. Moreover, this classification is super simple. All finite dimensional vector spaces are classified by their dimension. So, to know what a vector space looks like, all you need to have is one little piece of information, the dimension of this vector space, which is a positive integer. For example, if I ask you, what does this vector space look like? And you tell me 3. Then I'm like, oh, I see. So it's just like a copy of C3. Here is a formal statement that establishes this classification. Two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. We already know this statement in one direction. In one of the earlier videos, we have proved if vector spaces are isomorphic, then they have to have the same dimension. It is the opposite implication that is new here. So, assume we have two vector spaces U and V, and they have the same dimension. Let n be the common value of this dimension. Then we just proved that the vector space U is isomorphic to Cn, and the vector space V is isomorphic to Cn. These isomorphisms are given by vector representations. But isomorphisms of vector spaces are invertible linear transformations. In particular, we can construct the linear transformation S inverse that goes from Cn to V. In an earlier video, we have proved that the inverse of an invertible linear transformation is an invertible linear transformation itself. And then we can construct a composition of T and S inverse. This composition will go from the vector space U to the vector space V, and it is an invertible linear transformation because it is a composition of invertible linear transformations. So we have constructed an invertible linear transformation that goes from U to V. This means U is isomorphic to V. And we have proved that if two vector spaces have the same dimension, then they are isomorphic. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss matrix representations of linear transformations. I will see you later.